Okay, good morning, dear friends. I'm Professor BVNSS Prabhakar, working as a assistant professor under selection grade, VET Chennai campus. Today we are discussing system programming. This is for MS Software Engineering students. The course code is SWE 403. So system software is the broader area. So system programming is a part of that. So system software, an introduction to system programming. Linal Elbach, edition of slide, 1997 version. Later, as per the standards of the Indian students, they modified the revised version, developed. The Linal Elbach joined with Dr. T. Manjula, the senior professor in Anna University. So this is the prescribed book. So this book, if you follow, the Pearson Education, a low priced edition available. So this book is one of the best books. Apart from this book, we can follow different books. For any clarifications, students at any moment, they can reach me on mail prabhakar.vag.sc.in. So system programming, if you go to the course details, as per the textbook we have different chapters, but here in the chapter 1 we will discuss the background, the so-called machine architectures. Then in chapter 2 we will discuss assemblers. In chapter 3 discuss loaders, linkers, editors, debugging schemes. In chapter 4 microprocessor. Chapter 5 compilers. So operating system and other engineering, software engineering tools, engineering issues and all comes under this system software or system programming, but will mainly focus on machine architecture, assembler design, compiler design, microprocessor, loaders, linkers, text editors. So students should follow the scheme called PBL, project based learning. They have to identify a good problem in this system programming area. They can form the teams, team size minimum 2, maximum 3. In extreme cases they can go for 4 also. CAT 1 portion is first 2 units, machine architecture and assemblers. CAT 2, loaders, linkers, editors, microprocessors. Termed examination, now we termed as FAT. So final assessment exam or test, there will have all the 5 units. So for PBL we have 3 reviews, review 1, review 2, review 3. You need to submit your review with a report. All members should attend. Then that will be considered as your internal marks. PBL 20, CAT 1 will conduct for 50 marks, the weightage will be given 15. CAT 2 will be conducted for 50 marks again, weightage will be considered as 15 again. So 15 plus 15 plus 30 plus 20 PBL, 50 marks, this is internal. For term and or the final assessment test, we will be writing for 50 marks. 100 we will attempt, but weightage will be 50, together 100. The grade will be decided. For this course we have the lab component, system programming lab. The course code is SW404. If you get the concepts, you are familiar with this, then we will develop different programs like assembler, 1-pass assembler, 2-pass assembler, microprocessor, lexical analyzer, syntactic analyzer, semantic analyzer, and parse, top-down parser, bottom-up parser, recursive descent parser. Like we have different programs in lab that we will separately discuss. So as a prerequisite, what are the things that are required? So today we will mainly focus on the chapter 1. So in this outline, introduction, the introduction to system programming as well as system software, What is connection between system software and the machine architecture? There will be different machine architectures. We have independent machine architectures, dependent, when we will call the machine is dependent, when we will call the machine is independent. So all these things will come here. And apart from that, we will take a hypothetical machine, the hypothetical machine called SIC, the simplified instructional computer. So here SIC, we have SIC machine, SIC XG, extended version machine, and we will discuss different sample programs here. Apart from that, we will follow some traditional architectures like VAX, Pentium Pro, Cray 3-tier architecture, all these things. So that here CISC and risk reduced instruction set computer machines, SISC machines will be discussed at length. So what are the prerequisites are required? It's very simple. You should know the minimum basics in computer architecture. Once you know the computer architecture and organization details, probably if you're good in microprocessor, like microprocessor 8085, microprocessor 8086, 8088, 80286, 80386, 825, 805. Some areas, if you are strong, it will be good, so that you are familiar with sample programs. So it's very good to deal with. Similarly, you should be familiar with at least one high level language program such as C or C++, Java, anything. So if these two prerequisites, then you should have good knowledge in hexadecimal number system. You are familiar with decimal number system, binary number system, octal, hexadecimal, and so moreover we will use the binary and hexadecimal number system. This is the prerequisites. If you are strong in this area, it's more than sufficient. People will get good knowledge in that, apart from the grade. Now let me define a system software. So system software consists of a variety of programs that support the operation of a computer. You might study C or C++, you might study Java, you might study microprocessor, microcontroller, and all. So now the thing is, if you want to think about the operation of a computer, apart from the operating system, we need to discuss some of the programs. Such programs will be the part of the system software. So system software consists of a variety of programs that support the operation of a computer. So the program implemented in either software and or a firmware that makes the computer hardware usable. The software makes it possible for the users to focus on an application or other problems to be solved without needing to know the details of how machine works internally, like basic input-output systems and all this. We will discuss in detail. System software and machine architectures. What is the difference between system software and application software? It's very simple. One characteristic is which most system software differ from application software is machine dependency. So machine dependent, machine independent. So application software is a machine. Based on that dependency, we will differentiate. So system programs are intended to support the operation and use of the computer itself. See, if I want to run a program, then I need a system software. If I want to execute a program, I need a system program. If I want to load some content into the memory, I need a system software. So like this, of course, interchangeably we may use system program and system software. So what are the examples of system software? Text editors, assemblers, compilers, loaders, linkers, debuggers, microprocessor, operating system, DBMS, database management system, software engineering tools. Now let me define text editor. What is text editor? To create and modify the program. So text editor, you might know that if you want to run and write a C program, where we will write the C program, we want an editor, we will call it a C editor, or you might study it in Ubuntu and or in a Linux operating system and all, VI editor. So these are all different editors. So without editor, where we will perform like operation called copy, paste, cut, or we want to do some image, want to modify it, where we will do with an editor. If you want to apply a save command, save as command, and if you want to create a new document. So these are all the different operations of the text editor. So without text editor, we can't provide an environment or interface to the end user. So the end user, if they want to write their own programs, then text editor is the main platform. It is the main source. Through that only the programmer will write his own program and they will try to execute in time. So compilers and assemblers, say right from the inception of the computers till date, we are dealing with different programming languages and all. Of course, all the programming languages are super extremely, so every program has its own advantages. So here the point is not to discuss in detail about the drawbacks of the programming or comparing the programs. So whatever be the program, irrespective of the programming language, is the machine is going to read, is the machine is going to understand, or someone is going to help as and when system fails to understand that. So the point is here, when we are writing a program, 99% of the cases the system may not perfectly understand what the user or a programmer intention. That means the programmer, if he writes a program, the system may not be in a position to understand or digest it. Then we need someone to translate it. So the job of the compiler and an assembler is to translate the given program into machine readable language. Now the point is, if you take an assembler language, the input is assembly language, it generates its equivalent machine code. Similar, if you take the compiler will receive an input as a high level language program, then it will translate into its machine language or machine code. Say if you take a C++ program, you wrote so many steps. Now what is the duty of the C++ compiler? It takes the file as input, the C program as input, it translates its equivalent machine readable one. That is the job of the C++ compiler. Take a C, the same. So Java program will be given to the Java compiler, Java, then it will convert into its equivalent. Of course, in the case of Java, we will use Java compiler, Java interpreter, then the bytecode will be generated, but whatever it is, the translation remains same irrespective of the programming language. Similarly, the job of the loader and linker. Say, people will think that the compiler will compile it. Compile it means it translates, it generates its machine code. But who will prepare for execution? Who will take care of burden? So in turn, the linker will receive that machine code and it will prepare for execution. So the loader and linker, the resulting machine program was loaded into memory by the loader and prepared for the execution by the linker. So a linker, loader, they works together. The resulting machine programs was loaded into memory and prepared for execution. Now debugger. to help detect errors in the program. We know that there are so many errors. Sometimes humans intentionally, unintentionally, they may commit some mistake, something wrong. Then the debugger, it will remove all kinds of bugs, sometimes errors, sometimes linkage problems. So that's what when you are writing a program. So a text editor, it provides a platform to write a program. An assembler or a compiler will receive such a program and it will translate into machine code. Then the loader, it will receive and it will load into the memory. And linker, it will same program will be prepared for execution. So the debugger, meanwhile in the process of translating and the process of compiling or in assembling, if any error came into the existence, that will be solved by the debugger. This is what, if you see the complete what is the concept of system software, we will probably may understand in a better way. Now if you say the by machine in the computer, the whole part, this part is the whole machine, above machine we have. Now we know the operating system. So operating system is an interface between computer and its user. It provides a platform. It works like a resource manager. It acts like a virtual machine. So now it provides the environment platform. Now above machine, then we will use on the top operating system. You all might study the operating system as a separate course. In this system software, we don't want to discuss operating system, but operating system, the mind like memory management, process management, device management, information management, extra, a lot of things are there. Operating system. Now operating system will provide an interface between the user. Now if you go to the next level, now operating system will use machine hardware components and all. Now if you write something, if you see this is operating system based level, you will see the top user, they will interact with the system with the help of application program. Say you are writing something, you are using a banking system or anything you are using, a railway reservation, anything you are using. So the user in turn, they are interacting with the computer by means of application program. Now the application programs, where we will develop, we will write this one in the text editor. Now the text editor, we may not write the whole thing, say in C++, hash include stdio.h, hash include conia.h, void main. Now hash include math.h. What is this header file? Sometimes we want some kind of library functions and all. So all the utility programs will be get from the library. So the text editor, when we are writing some header files and all, these will be getting from the library. Sometimes the programmer feels tired, or some routine jargon is there, some repetition is there, then they can use the macros. That means repetition statements they can find. Then instead of repeating the same, we will define a macro. Then we will use macro processor. The macro processor will substitute that thing. Then that pure ALP will be supplied to the assembler, of course to a compiler. We will discuss in chapter 4 microprocessor in different. Friends, here I am telling one thing, microprocessor is different, macroprocessor is different. Microprocessor, programmer will write a program his own way, as and when they fail to define something in a shortcut way, they will write something so that the shortcut will be substituted at the time of before submitting to the assembler or a compiler. But whereas microprocessor is a central processing unit of a microcomputer. So don't confuse with the microprocessor role with a macroprocessor. Now we will use debugger as we discussed in the previous slide. Debugger role, when you write something, before beginning, if it is not understanding, then debugging will be happen. Now a compiler, we know that high level language program will be translated into machine. Assembler, we know that ALP will be as input and generate its machine code. Loader, it will load the content into the memory. Once you convert into the machine code or machine language, that will be loaded into the memory. Linker, it will prepare for execution. So this is what the broader spectrum. Now a bare machine hardware, a computer design we don't want to discuss. Operating system, this course it's not the objective to discuss operating system, this operating course. Now this area we will discuss starting from emission architecture. Application programs, our job is not to discuss application programs. Assemblers we will discuss, that is chapter number 2. Compilers we will discuss, that is chapter number 5. Microprocessor we will discuss, that is chapter number 4. Loader, linker, text editor, debugger we will discuss, that is chapter number 3. So on the whole, what kind of architectures we want, machine architectures we will discuss chapter number 1. Here chapter number 1 means as per the back textbook we have all the things, so all the textbooks. So the system software and the machine architectures. So before going to the machine architecture, mission dependent, mission independent. So what is a mission dependent? If you take the computer, a mission dependent things are there, a mission independent things are there. So mission dependent means with respect to the machine we will define the instruction set, we will have instruction formats, we will have addressing modes, we have with respect to instruction set, instruction format, addressing mode, we have assembly languages. Similarly we have mission independent. So mission independent means so design logic, strategy, 2-pass assemblers, like 2-pass means there will pass 1, 2-pass assembler means pass 1 of 2-pass assembler, pass 2 of 2-pass assemblers. Like microprocessor also we have 1-pass microprocessor, 2-pass microprocessor, pass 1 of 2-pass microprocessor, pass 2 of 2-pass assembler, like different things like loaders, linkers. Now here the main thing, if you take the machine architecture, if you take a computer, mission dependent computers are there, mission independent computers are there. So the mission dependent computers will take care of instruction set, instruction format, addressing modes, assembly languages. With respect to all, how many, what are the size of that, how many registers are there. So 8-bit registers, then what about the instruction set, 16-bit register, what about the instruction format, and sometimes some machines like 8085 is 8-bit register, 8086 is a 16-bit register, 8088 the best example of 8088, this is a 8-bit come 16-bit register. So like this, all these bit register size, 8-bit microprocessor or 16-bit microprocessor, these are all machine dependent, sometimes machine independent. So how we are taking respect of the above all register size and all, we will discuss whether it is 2-pass or 1-pass, how we are designing general strategy. This is what, it's very simple. We will discuss this area. Now in general we have to take a machine, a real machine, then we have to work. Now let me ask a small query to you guys. Say for example your job is, you are working as a great engineer, you are given crores of rupees. Now you have to go and design a missile or a rocket, a water tank. So then your boss or your supervisor will allow you to design the same thing, or in a simulated way, in a simulated manner we will take a small scaled one and we will try to say, if you want to design a helicopter big one, before that at a small scale we'll take the small thing, then we will check the functionality, behavior, how it is performing, then we will try to know that. That's what the simulation. You might study it in future, they might study it, I don't know about that course, might not. Okay, of course that's different part, but anyhow the point is here. So we will know that when we are going to develop something, there is no guarantee we will go with the actual machines. So first we will try with the small. Say if you want to be a champion, or if you want to be if you want to swim in Pacific Ocean, then directly will go and swim now. No, first you will find a pond nearby you or a swimming pool based on your height, based on your age, then you one by one, just like you go and learn swimming, then you will be allowed to participate. So similarly, so here we will take in a small example a hypothetical machine, a hypothetical computer that we will work. Okay, so that's what the simplified instructional computer. Like many other products, SIC comes in two versions. One is the standard model and an extra equipment or extra expensive version like XE. The two versions has been designed to be upward compatible. First, let me explain SIC, simplified instructional computer. SIC is a hypothetical computer that has been carefully designed to include the hardware features most often found on real machines while avoiding unusual and irrelevant complexities. Then simplified instructional computer SIC with extra equipment, that's called SIC XC. So we have two variants throughout this particular chapter, probably for machine architecture chapter 1 unit 1, assembler chapter 1 unit 2, and loader linkers chapter 3 unit 3, and microprocessor chapter 4 unit 4 microprocessor. Also we will discuss SIC XC2 versions. We will discuss what is a simplified instructional computer. It's very simple. Upward compatibility is there. A memory consists, see, if you take any machine, the machine should have a memory, should have the registers, we should discuss the instruction set, we should discuss the instruction formats, addressing modes. These are the basic things we will discuss in first chapter. So a memory consists of 8-bit bytes. If you want to represent a word, that is 24 bits of length, probably 24 means 3 8s are 24, so that 3 consecutive bytes will be reserved for maintaining a word. There are a total of 3268 bytes, 32 KB in the computer memory. So it's a very small hypothetical computer. That's what we discussed in the introduction itself. So it's a 32 KB, that means 32,768 bytes we will reserve memory. So now in this machine we will discuss 5 registers, each register 8-bit bytes, that means 24 bits in length. So if you take any machine, we have to use a processor register, that's called a principal register, that's what accumulator. And for the sake of better understanding and for other conversation, we will give number for each register. So the number given to accumulator is G and it will be denoted with A, and we will use an index register X. Index register X number is 1, and we will use a linkage register, probably we will use an instruction called JSON, there we will use a linkage register L. We will use the program counter PC, the number is 8. Status words or condition flags will be used, the number will be 9. So in this particular SIC we will discuss A accumulator, index register, linkage register, program counter, status word. Now you may ask, sir, 0 1 2 given, 8 9 given, what about 3 4 5 6? Yeah, for SIC XE we will take some other register like B, S, T, we will discuss. Okay, so all the numbers will be given later. Now what are the data formats by SIC machine architecture? So the machine architecture, what data formats it will support? Integers are stored in 20-bit binary numbers. We will accept 2's complement representation. Say if you want to use a negative number for binary operations like addition we need addition, but sometimes addition also requires, you know one thing. So if you want to subtract a number 5 minus 7, how we will do that? 5 minus 7, so 5 plus minus 7, 5 plus within the parenthesis will write minus 7, that's what the interpretation. That means 5 we are taking, then we are adding with the minus 7. How we will represent that? How we will represent minus 7 in binary? That's the only way, 2's complement representation. So All negative values will be represented with choose complement. Then we will use different characters. Whenever we are using characters, we will use ASCII codes. Of course, in this SIC, no floating point will be used, but these floating points will be accepted by SIC XC. Now, if you take an instruction cycle, if you take any instruction cycle or any instruction will be executed by the CPU, central processing unit, with the support of the CPU consists of three things. One is the control unit, probably in other areas we'll call timing and control unit. It will register all cycles one by one, timing cycles. And we will use arithmetic and logic unit, ALU, and we will use registers, different registers. That's for the CPU. All arithmetic and logical operations will be performed by ALU with the help of the register. The registers further we classify working registers, general purpose registers, status registers. Like I think in previous slide we discussed status word SW, or we studied a register called PC, program counter. What is the responsibility of PC? Means it holds the next address of the instruction to be executed. So like all the registers will. So the CPU will respond. Instruction cycle. In instruction cycle we have fetch cycle, execute cycle or execution cycle. Normally if you take these two, further we can divide into three things. One is the fetch, decode, then execute. This is what we might study in computer architecture or in computer organization, like Maurice Mano and other books. They explain nicely about instruction cycle. So in the instruction cycle we have the fetch, we have decode, we have execution. Now the same thing we explain in different way. First we will fetch the instruction, then we will decode the instruction, like we know opcode, operation code based on the mnemonic. Then we will try to fetch the operands. First we will fetch the instruction, then we will decode as per the mnemonic code or opcode, then we will fetch the operands from the memory. Then we will go for execution, that's what the computation. Then finally we will store the result. This is what the instruction cycle. Next, if you take the SIC machine architecture, as we discussed, it's 24-bit format. Now if you take the 24-bit format in any instruction, we will classify in two parts. One is the opcode part, that's what opcode. Then we will use X, then we will address. So the flag bit X is used to indicate indexed addressing mode. So opcode 8, X1, address 15. So next class we will discuss addressing modes. Thank you.